Good afternoon. Just picking up where we have left off in the case of working with compositions between functions, and for the group of exercises from this particular area, we had, starting from page 225, we looked at 10 through 26 even, where we had operations of various types among functions, and now looking further into the composition of functions, and we have starting with number 47. Okay, we're looking at compositions, functions at specified inputs. And for what we have in the case of number 47, so we have f composed with g of x, whereupon x is equal to 8, and just writing this in completely functional terms. Okay, so the circle separating the f from the g, this is in reference to composition, not multiplication. Okay, so for f composed with g of 8, okay, we're going to have f of g of 8 and for what we have in the case of the input g of 8, we can get a specific numerical value for g of 8, for we can reference g of x, okay, whereupon x is equal to 8. So we go ahead and determine the value of g of 8. Okay, so g of 8, okay, we have the square root of 2 times 8. And 2 times 8 is 16. And we have that the square root of 16 is equal to 4. Okay. And so f composed with g of 8, okay, we have that f of g of 8, and that translates out to f of 4. And in the follow through, okay, so we have with f of 4, okay, so we'll operate along the lines of f of x. So f of the input is equal to the cube of the input minus 4 times the input. And with x set to 4, we have f of 4 is equal to 4 cubed minus 4 times 4. And carrying out the operations, 4 to the third power is 64. Negative 4 times 4 is negative 16. And 64 minus 16 comes out to 48. So f composed with g of x whenever x is at 8 comes out to 48. All right. Now, for what we have in the case of number 48, problem 48, okay, we're now looking at h composed with g of 2. And in this one, okay, so we have, again, have h composed with g whenever x is at 2. So this will become h of g of 2. And just like what we did with g of 8, okay, we can go ahead and evaluate g of 2. Okay, so referencing again g of x, we have g of 2 is going to be the square root of 2 times 2. 2 times 2 is 4, and the square root of 4 is equal to 2. And just taking what we have and following through, so we have for h of g of 2, so we have h of 2, and for the h function, okay, this time we have h is a linear function, where h of the input is equal to 2 times the input followed by the addition of 3. And with x at 2, okay, we'll have 2 times 2 plus 3. And so we have in the follow through, okay, so we have 4 plus 3, and h composed with g of 2, this comes out to 7. Now, for what we have in the case of 49, so we've had working with f and g, h and g, Now if we tie in together, okay, a composition where we have interaction between F and H, and we have for number 49, okay, we have H composed with F whenever X is set to 1. So for H composed with F at X is equal to 1, okay, so this is going to be H of F of 1. And again, just going ahead and identifying the numerical value of the input. Okay, where we have F of 1. Okay, so referencing F of X. Okay, we have the cube of the input minus 4 times the input. And 1 cubed is 1. And negative 4 times 1 is negative 4. And we have 1 minus 4. And that is going to be at negative 3. And so for H of F of 1, this is going to be H of negative 3. And utilizing H of X again. So H of negative 3 as the input, we're going to have 2 times negative 3. Followed by the addition of 3. Okay, 2 times negative 3 is negative 6 plus 3. And so we have H composed with F of 1 is going to be negative 3. Now, for what we have for number 50, okay, this time we're looking at interaction once again between F and G. And we had the reverse of order of number 47, where we have G composed with F, and the input value is going to be at 3. And let me just reapply these functions. Okay, so we have our F of X, G of X, and H of X once again. And for number 50, okay, so we have G composed with F whenever X is equal to 3. Okay, so we're going to have in this one, okay, so we have G of F of 3. And for what we have in evaluating F of 3, okay, so F of 3 is going to be 3 cubed minus 4 times 3. 3 cubed is 27. Minus 4 times 3 is negative 12. And 27 minus 12, okay, is equal to 15. And so that would be used to fill in as the input. So here we have G of 15. Once again, for the output function which we now have at G, we have G of X is equal to the square root of 2x. And we have with G of 15, we have the square root of 2 times 15. And for the output, and leaving in exact terms, okay, this comes out to the square root of 30. And in spite of being a rather high even number, the highest perfect square divisible into this is only 1. Okay, so the square root of 30 is already in simplest radical form. Right. Now, for what we have still working with FG and H of X. Okay, now we have in the case of number 52. Okay, so we're now looking at F composed with H composed with F when X is at negative 1. So in this case, we're going to have H of F of negative 1. And looking at F of negative 1. Okay. So again, we have with f of x with x at negative 1. So we have negative 1 cubed minus 4 times negative 1. Negative 1 cubed, again we have minus 1. Negative 4 times negative 1 is 4. And negative 1 plus 4 comes out to 3. And applying this as input. Okay, so we have h of 3. Again, so we have with utilizing the h function, which again is 2 times the input plus 3. And we have with the input x, now at 3, we have 2 times 3, which is 6. And 6 plus 3 is going to come out to 9. Now, for what we have in the case of working with, again, g and f. So we have g composed with f whenever x is at 5. Okay, so we're going to have g of f of 5. And evaluating, first of all, f of 5. Okay, so we're going to have, once again, the cube of the input minus 4 times the input. And with the input at 5, okay, so this comes down to 5 cubed, which is 125. And subtracting 4 times 5, so we have minus 20. And so we're going to have f of 5 equal to 105. And plugging back in, okay, so we have g of 105. Okay, we have g of the input is equal to the square root of 2 times the input. And for this one, okay, so with the input at 105, okay, so you have the square root of 2 times 105. 2 times 105 is 210. And we have for the exact result, okay, this comes out to the square root of 210. And this is a little bit of a surprise too, but 210 is already where the square root is already in simplified form. So 210, you have a much larger number than 30. It's also even. And it turns out that the highest perfect square divisible into it is only 1. I mean, think of like 4, 16, 36 among the other even values, and none of them will be completely divisible into 210. Okay. All right, now in the, yes.
For 52, it's f of h.
F of h. Okay. We can do that.
I got it. Okay. I got it wrong. I just want to make sure.
Okay. This is gonna be h of f.
Okay.
Yeah. At least the book I have has it as h composed with f. Okay. All right. Now, for what we have in the case of the next item. Okay, so we got for once again just taking what we have with f, g, and h. I'll tell you what, we'll do this again. Let's say we have f of h of negative 1. We'll do that too. Okay, so if I were looking at f of h of negative 1, okay, so your h of negative 1, okay, so this would be 2 times negative 1 plus 3. 2 times negative 1 is negative 2. Negative 2 plus 3 comes out to 1. So we have in this case, okay, so f of h of -1 with h of 1 leading up to 1. So this comes out to f of 1. And in the follow through, so referencing f of x, so we have f of the input is equal to the cube of the input minus 4 times the input. And so we have with the input at 1, so we got 1 cubed minus 4 times 1. 1 cubed is 1. And we have minus 4. So in this case, we have the output at minus 3. Okay, so, and sometimes the order can make all the difference, okay, because we have with h composed with f of -1, the output was at 9, but reversing the order for these functions, okay, we have the output to land at -3. All right, now in the case of the next group, okay, now we have going from fg and h of x to different letters, okay, still with the general input at x. And we have with the different letters, okay, for the outputs. Okay, so we have m of x, and this is presented as a radical function whereupon m of x is equal to the square root of x plus 8, and we have n of x is equal to x minus 5, and we have p of x. Okay, we have that set equal to x squared minus 9x, and then finally we have with q of x, okay, that is given as the reciprocal of x minus 10. And so for what we have in the case of 65, okay, now we're looking at the composition as well as the domain, okay, and again for the domain of compositions, again, you have playing by a different set of rules. Okay, you're looking at the domain of the input as well as the domain of the final output, namely the composition result itself. Now for what we have in 65, okay, now we have n composed with p of x. And I'm just clustering, okay, so this becomes n of p of x. Okay, and if we specify what p of x is, okay, so we're looking at n of x squared minus 9x, okay, and in terms of going about and following through, okay, so again, your output function is n, and n of whatever the input is going to be that input minus 5. Now for working with p of x at x squared minus 9x, okay, we have in terms of the follow through, okay, the input minus 5, okay, it's not x minus 5, but instead we have x squared minus 9x. Followed by the subtraction of 5. And once I remove the parentheses, no sign change, no like terms to combine. So here we have x squared minus 9x minus 5. And as for the domain, okay, again, we have with the input is at n squared minus 9x. X squared minus 9x, okay, so I don't have a fraction, I don't have an even root radical, so the input itself, I'm going to say NR for no restriction, okay. Input has no restriction, and in terms of the final output, we have the final stage, the composition itself. We don't have any fraction. We don't have any even root radical. So for this statement, okay, I can plug in anything for x. Okay, so this also has no restriction. Okay. And since we have both the inputs and the final output have no restriction, we have altogether there is no restriction at all. All right, so we got for the domain of this composition, since there is no restriction at all, that means that the domain is going to be the set of all real numbers. Right. Now, still, okay, with these functions, okay, we have for the next situation. Now we've got with the involvement between the functions p and n, and just looking at what we have here. So I'm just going to go ahead and copy these functions. Okay, so in 66, okay, so I had p and n to work with. Okay, so you got the reverse order. N composed of p of x. We have x squared minus 9x minus 5. And 66, I'm reversing the order. So for p composed with n of x, okay, so I have p of n of x. Okay, and I can go ahead and specify the input. Okay, so n of x, we have x minus 5. Okay, and in terms of following through, now before, when I had the functions in reverse order, the output function was in accordance with n of x, but now it's going to be in accordance with p of x, whereupon p of the input is equal to the square of the input minus 9 times the input. Okay, and so with the input at x minus 5, so the square of x minus 5, and have minus 9 times the quantity of x minus 5. And just following through, now just work down. For the square of x minus 5, and we have x squared minus 10x plus 25, and negative 9 over the quantity of x minus 5. We got negative 9x plus 45. And joining together like terms, have x squared, negative 10x, and negative 9x. So this would be a negative 19x. And 25 and 45 will make 70. And so looking at what we have for the domain, okay, now for x minus 5, okay, so you have a bit of history to repeat. It's a different input, but again, there's no even root radical or fraction, so there's no restriction. And likewise, we have with the final output, we have no restriction. So between the input and the final output, again, we have no restriction at all. So in this case, we're going to have for the domain, okay, that's going to again be the set of all real numbers. Okay, now for what we have in the case of number 67, Okay, this time we're looking at intermingling the functions m and n. Okay, so we have our first appearance of m in the group, and for 67, okay, we're now looking at m composed with n of x. So just looking at clustering together, so we have m of n of x, and n of x, okay, we have x minus 5. And for the follow through, okay, again, we have the output is going to be in accordance with m of x, where we have m of the input is equal to the square root of the input plus 8. So for m of x minus 5, okay, so I have the square root of the sum between x minus 5 and 8, and we have constants to combine, and what's going to happen here is that we're going to come out to x plus 3. So the output is going to be a radical term, and now looking for the domain of this particular composition. Again, for the input, there's no contributing restriction. However, for the final output, okay, we do have the restriction that since we have a square root this time around, before all of our outputs were in direct terms regarding x. Now with the square root, okay, of x plus 3, so x plus 3 cannot be negative. Now it can be 0 and it can be positive. So we just have setting up what is allowable, okay, for x plus 3 in terms of a comparison to 0 inequality. Okay, so we have x plus 3 is greater than or equal to 0, and looking at solving for x. Okay, so if we take 3 away from both sides, we want to have that x is greater than or equal to negative 3. Alright, so again, the input has no restriction. In the case of the final outcome, okay, we have x is greater than or equal to negative 3. So we have for the only restriction, again, we have the x is greater than or equal to negative 3. And just taking what we have here. Okay, so the centerpiece number, okay, we have at minus 3. And again, with the equal sign, negative 3 is included. And the rest of the values will be greater than. And so there will be a ray that goes out to the right. And we have heading toward infinity. So the domain of this particular composition expressed as an interval notation expression, okay, representing x is greater than or equal to negative 3. So you're going to have a bracket to enclose negative 3. And again, for the rest of the values, okay, we have to be greater than negative 3. And we have continuing out in the direction of positive infinity. Right. Now, for what we have in the case of still working with these functions. Now we have just reversing the order. Okay, we had m composed with n of x. Now, in the reverse sequence, okay, if I have n composed with m of x, so for n composed with m of x. Okay. So I have n of m of x. And m of x, okay, our input, that is going to be the square root of x plus 8. Again, just for the follow through, again, we have the output function at n, where we have n of the input is equal to the input minus 5. And there's really not much to do here, okay, because input is the square root of x plus 8. And have the minus 5 to come right after the radical term, and there's nothing to combine here. So your resulting composition is going to be this difference between the radical expression and the number 5. Okay. And in terms of what we have concerning the restrictions, okay, so we have with the input, which is now the square root of x plus 8. Again, just a bit of history that repeats. Like what we had with x plus 3 moments ago. Okay, so x plus 8 cannot be negative, but it can be 0 or positive. Okay, so you have the x is greater than or equal to negative 8. So that is the restriction from this. And in terms of the output itself, guess what? The restriction comes from the square root of x plus 8. Okay. And so for the input and the output, okay, the restrictions are identical. Okay. And so just setting it up. Okay. We have for the domain, okay, the inequality that defines the domain. Okay, we have x is greater than or equal to negative 8. Negative 8 is included. So once again, we have a solid point to start out with, and the rest of the values can be greater than, so we have, once again, an array that's going to go out to the right. And so again, we have for the domain of this particular composition, okay, we're looking at going from and including negative 8, which will be in the bracket, and then we have out to positive infinity. Now, in looking at what we have now, just to kind of mix things up a little bit, we've not utilized Q of x yet. and 70. Okay, it's going to lead into this. Okay, let me I'm going to get these four functions again. Okay. In the case of 70, we have Q composed with P of X. Okay. And so we have in the formation case, we have Q of P of X. And specifying case, so the input, we have a P of X, okay, which is going to be X squared minus 9X. And for the follow through, and in accordance with Q, where Q the input is equal to 1 over the input minus 10. Okay, so the input, we'll have it X squared minus 9X. Okay, so 1 over X squared minus 9X, okay, followed by the subtraction of 10. And that's going to be the final output. Now, for what we have for the domain, now X squared minus 9X, okay, you don't have a fraction or an even root radical, so that on the input side, okay, we have no restriction. And now for the final output, okay, we're going to have some restrictions, okay, for since we have in the denominator. In this rational function, we have an expression that cannot be equal to 0. So we have X squared minus 9X minus 10 cannot be 0. And if this cannot be 0, well, the factors cannot be 0. And the factors of the trinomial, so we have X plus 1 and X minus 10. And looking at specifically what would be excluded. Okay, so if X plus 1 is not allowed to be 0, well, we have the X cannot be negative 1. And for X minus 10, if this cannot be 0, well, we have the X cannot be equal to 10. Okay. So combining the restrictions from the input as well as the final output. Okay. All the restrictions come from the final output. So we have the X cannot come out to negative 1, and also we have the X cannot equal 10. And so for the domain, okay, so we're leaving out negative 1 and 10. So negative 1 is excluded. So it's 10. Okay, but everything else between, before, and after will be in the set. Okay, so for the pieces, have a ray going to the left, a line segment in the middle. And for the rest, okay, we have a ray that's going to go continuously to the right. And so for the domain of this composition, okay, we're going to have three sections. Okay, and we have at the lower end, okay, so we have going from negative infinity and approaching but not including -1. We have next represented by the line segment. Okay, we have a set of values x between but not including -1 and 10. And for what we have at the upper end, we have those values of x greater than 10. All right, so you have three separate sections in the interval notation for the domain. Now, one more item from this set, and this is where you can have composition between a function and itself, and 76 is such a case. And for what we have in the case of 76, okay, so we're going to have P composed with itself. Okay, so you have P composed with P of x. And so we're looking at P of x. Now for this part, this is arguably more an exercise for the eyes than anything else. Okay, but for P of x, input is at P of x. So we have specifically, okay, we have P of x squared minus 9x. Okay, so P of x is the input, and the output, okay, is going to be in reference also to P of x, where P of the input is equal to the square of the input minus 9x. And so we have in following through, okay, so we have x squared minus 9x, okay, and looking at applying x squared minus 9x as the input, not the defining output, we have x squared minus 9x to the second, and we have minus 9 times all of x squared minus 9x. And so for what we have in following through, so squaring out x squared minus 9x, so this will be x to the 4th minus 9x cubed minus 9x cubed, and the square of negative 9x, okay, so that's going to be a positive 81x squared, and we have minus 9x squared, and we have plus 81x. And looking at gathering the like terms, okay, so we have x to the 4th in the cubes, okay, we have negative 9 and negative 9 for the coefficients, so that will add up to negative 18x cubed. And for the squared terms, we have 81x squared minus 9x squared, so we're going to have a 72x squared. And the last term would come out to 81x. Okay. So the resulting composition here is going to be this 4th order polynomial. And so for the domain of P composed with itself, input has no restriction, and for the final composition, okay, you don't have an even root radical or a fraction, so there's no restriction from that either. And so again, we're back to where we have for the domain of the composition, okay, that is going to be the set of all real numbers. Okay. Now, looking ahead, now we've been looking at operations between functions. and just sort of not so much backpedaling, but just looking at individual functions through another capacity. And so we'll be looking at all kinds of categories among functions. Okay. And again, a function is where in the xy coordinate system, for every x value, there's only one corresponding y value. And we looked at stuff like domains of functions, and for sets of ordered pairs, we have like domain of a function, range of a function, range being the set of y terms. We've looked at function values, and again, most recently, operations between functions. And now looking at categorizing, and this will be sort of like an early sneak peek into some of the stuff you might encounter in Math 172, should you take the class. And this will be with what we have with odd and even functions. And for what we have in the case of odd and even functions. Okay. Now, first of all, for an odd function, okay. Now, an odd function is going to be a function that has symmetry or is reflected about it's going to be reflected about the origin, that is, where x is 0 and y is 0. And it is going to be defined by the following relation. Okay, and this is going to be where we have f of negative x is equal to the negative of f of x. Okay, and what does this mean? Okay, well, for odd functions, you have this relation. Okay, and what this means, you have, for the input, you have negative x and positive x, and then for the outputs, you have a positive f of negative x, but on the other side, you have a negative in front of the f of x. So what does this all mean? Well, for odd functions, this means that opposite sign inputs will lead to opposite sign outputs. And for what we have in the case of an odd function, okay, we can say that we have something that is along the lines of where we have f of x is equal to x cubed plus 2x. And where all the terminology is going to come in. Okay, so you got f of x is equal to x cubed plus 2x. Okay, so just looking at what we have here. Okay, so you got for f of x, Okay, so f of x is equal to x cubed plus 2x. And if I take f of negative x, and I take negative x and treat it as the input in accordance with f of x. So I'm going to have the cube of the input, which will be the cube of negative x. And we have plus 2 times the input. This will be plus 2 times negative x. And for the cube of negative x, okay, this will be minus x cubed minus 2x. And it's going to line up the terms here. So you got f of x. Again, we have an x cubed plus 2x. And just to mention, okay, so we have between the inputs, okay, so between the inputs you have x and negative x. Okay, so these are going to be opposite. And for what we have in terms of the output, and if you notice, okay, you have positive x cubed and positive 2x for f of x. But now for f of negative x, we have a negative x cubed and a negative 2x. So you have throughout, we have opposite sign inputs lead to opposite sign outputs. So if the outputs, okay, for additive inverse inputs, okay, if the outputs have all the terms to be like polar opposites, positive in one, negative in the other, then that means that f of x equals 2x cubed plus 2x. Okay, that is going to be an odd function. Okay, so again, this is a sample of what we have with an odd function. Now, just looking at what we have from a visual standpoint. Okay, so for f of x or y is equal to x cubed plus 2x. Okay, now you're going to have symmetry with respect to the origin. And I said that opposite sign inputs will lead to opposite sign outputs. And I did have somebody ask me a case like, where did these x and y values come from? And basically, now you got symmetry with respect to the origin. Okay, so just taking what we have for x, okay, so I chose 0, and then looking at what happens as you start to stray from the origin equidistantly. Okay, you have on one side you have going out to positive 1, the other negative 1, then positive 2, negative 2, so just kind of maintaining that pattern. Okay, so you got 0, 0. If you notice, we have with the additive inverses of negative and positive 1. And guess what? We have additive inverses with the outputs negative and positive 3. Likewise, negative 2 and 2, outputs you have negative 12 and positive 12. Negative 3 and 3, output you have negative 33 and positive 33. And if I were to go out further in the negative zone as well as the positive, I'm going to maintain additive inverses for the outputs. And now regarding the symmetry, okay, notice to the right of the y-axis, just as I am going up and to the right along the y-axis, again to the same extent in the negative zone, I'll be going down and to the left and very much in line with the lower region of the y-axis. Okay, so just I'm going up, just reflecting across the origin, like these two halves are mirroring each other, where this part is up to the right to the same intensity, that part is down and to the left. So this is a sample of what we have with an odd function. And I've had somebody in the past ask me, what is an odd function going to be one where the leading term is an odd power? And in a lot of cases it is, but just because the leading term is an odd power does not guarantee that it is going to be an odd function. Right. Now, in the case of even functions, okay, and there's a thin line between odd functions and even functions. And in the case of what we have for even functions, and even function is going to be a function that is reflected about the y-axis or has symmetry with respect to the y-axis. And this is going to be defined by another functional relation. Okay, and this time around, okay, we're still going to have f of negative x. Okay, now an odd function had f of negative x leading to the negative of f of x. But here for even functions, we have f of negative x is equal to f of x. Okay, so instead of a negative on the right, we have a positive f of x. So for what an even function signifies is that opposite sign inputs will lead to the same outputs. And just sample of what we have regarding even functions. Let's say we have f of x is equal to x squared minus 2. Okay, notice the even power. Okay, and one might also ask, will a function with an even power term at the front necessarily mean it's an even function? In a lot of cases it will, but not all situations. So just looking at the dynamics that we have here, so you have f of x is equal to x squared minus 2, and we'll take the opposite sign inputs. Go ahead and place the arrow so you have f of negative x. Now we got f of x is equal to x squared minus 2, and if I have the input at negative x, okay, so you got what's going to be the square of negative x, and no sign change for the constant since that is already locked in at minus 2. So the square of negative x is going to be positive x squared. We have minus 2. And just repeating what we have for f of x. Again, that is x squared minus 2. Okay, so the inputs, okay, those are going to be opposites. And for what we have in terms of the outputs, okay, if you notice, you have x squared on both, negative 2 for both. So these are going to be the same, and so for what we're going to have in effect is that f of x equals x squared minus 2 is an even function. Okay, so you have, again, opposite sign inputs for both cases, but if you have unanimously opposites, the function is odd. And if the output is unanimously the same, okay, then the function is even. And for what we have for f of x is equal to x squared minus 2, okay, so for this graph, okay, so for x squared minus 2, so again, just like with what we have for x cubed plus 2x, okay, so I just selected the same x value, so you have at 0, and then additive inverses negative 1, 1, negative 2, 2, negative 3, 3, and notice we have for the outputs, okay, so you have 0, negative 2, but for the additive inverse, you got negative 1, 1, negative 2, 2, negative 3, 3, and the outputs are identical. Minus 1 for both, negative and positive 1. 2 is the output for both inputs, negative and positive 2. And for the input values of negative and positive 3, we have the output at 7. Okay, and again, so you have your y-axis, and instead of going away from the origin, okay, we have straying from the y-axis. Okay, so you have at 0, negative 2, as you start to get out to the right and to the left, as you kind of get equal and horizontal distance away from the y-axis, you're going to be at the same vertical level. Yeah, like 1 to the left, 1 to the right, same level. 2 to the left, 2 to the right, same level. And again, for 3 to the left and right, also you have those points at the same level, and that is going to maintain course. Okay, and so you have symmetry with respect to the y-axis. Okay, and again, that is the characteristic in graphing for even functions, and just kind of doing a little bit of separating the odds from the evens and any other type of function. And let's say if you were to determine whether the function is odd, even, or neither. Let's see that we have possibly a little bit of a softball example. Okay, so if I have f of x is equal to x cubed, Okay, so I have f of x is equal to x cubed. And just plugging in, let's say the input as negative x. Okay, so I have f of negative x. And for the cube of the input, so I have the cube of negative x. And so this will end up as minus x cubed. So we have f of x is equal to x cubed. F of negative x comes out to negative x cubed. Let's take 2. There we go. Okay. So again, you have opposite sign inputs and the outputs. Okay, those are opposite sign as well. Okay. So in this particular case, right, this function is going to be odd. I'll say as a second case, right, if I have f of x is equal to x to the 4th plus 3x squared and look at f of negative x. Okay, so you got the 4th order of the input. Now if x is negative, an even power of a negative is going to turn out to be positive. Okay, so for the 4th degree of negative x, that comes out to positive x to the 4th. And the square of negative x is x squared multiplied by positive 3. So we're going to have another situation where we have x to the 4th plus 3x squared yeah, so you have opposite sign inputs. Let's see. Trying to get my colors right. Okay, so we have, in this case, right, so you have additive inverse inputs, and we have the same output unanimously. Okay, so for what we have here, for x to the 4th plus 3x squared, okay, so this is going to become an even function. And for what we have, let's say for f of x is equal to, let's say we have 3x to the 5th plus 7. Okay, only 2 terms here, but I think this will illustrate the point. Okay, so you have f of x is equal to 3x to the 5th plus 7. And for f of negative x, So you have 3 times fifth order of negative x plus 7. Now, negative x to the fifth, that's going to be minus x to the fifth multiplied by 3. So we're going to have a negative 3x to the fifth plus 7. All right. So again, we have for the opposite inputs, what's going to happen here, okay, for 3x to the fifth, negative 3x to the fifth, these are opposite. If you notice, we have with the constants that will follow, okay, these are going to end up being the same. And guess what? If you don't have unanimously the same or unanimously the opposite, what's going to happen here is, say if you got both, okay, there's a bit of static that is created. So if you don't have unanimously the same output where it is even, or unanimously the opposite output where the function is odd, but you got a bit of both, it's going to turn out that for this particular function, you're going to have neither odd nor even.